Okay, so the next topic we're covering is enzyme kinetics. For an enzyme that binds to one substrate, the catalysis pathway can be written as such, and we've seen this pathway before, so it's nothing new for us, where E equals to the enzyme, S equals to the substrate, ES is the enzyme substrate complex, EP is the enzyme product complex, and P is the product. So what does this look like? The kinetics of such an enzyme is shown below. So we have rate of the reaction right here as our y-axis. And we have substrate concentration as our x-axis. And you can see that as the concentration of substrate increases, the rate of the reaction increases until it reaches a Vmax right up here. Well, actually, it doesn't really reach the Vmax, but it gets close to it, correct? Why is there a maximum velocity? Well, there's a maximum velocity because there's only so much enzyme. And when you start getting close to the Vmax, like, in basically this whole area right here, what's happening is you're running out of active sites, meaning that an active site takes a substrate, it transforms the product, releases the product, and immediately another substrate comes in to bind to the active site. So you run out of empty active sites. And when you start running out of empty active sites, well, the reaction starts to get closer to Vmax because you just can't go any faster. And that is the maximum rate by which the reaction can happen. Now, you should have a basic understanding that Vmax is very dependent on the enzyme concentration, because if I have more enzyme, well, what will happen is that my Vmax will be higher. If I had less enzyme, let's say I have half as much enzyme, then my Vmax will be lower, so my rate of reaction graph will look something like this, right? And where my Vmax is lower, so my new Vmax would be here, right, and etc. But there is some data here that can be used, and we're going to talk about that. So we have Vmax, we also have this thing called half a Vmax, and half a Vmax is exactly what it sounds like. It's 50% of Vmax. And if you go from half a Vmax to this plot of the rate of the reaction as concentration of substrate increases, and you come down, you have the Km. So the Km is the concentration of substrate at which the reaction is happening at half a Vmax. Okay? Before we move on, I just want to show you guys a couple of things. I could have another enzyme that has the same Vmax but has a different Km. For example, I could have a second enzyme which has this sort of rate of reaction versus substrate concentration plot. Where now, with the Vmax being the same, if I go to from half a Vmax to here, you can see that, oh, the Km is different. So keep that in mind. So for the picture above, for the graph above, V is the rate or velocity of the enzyme catalyzed reaction as a function of substrate concentration. Vmax is the maximum rate, and Km is the concentration of substrate needed to reach a half a Vmax. If you're wondering how you can calculate V or Vmax, there's two ways. For example, let's look at a reaction A goes to B. Well, I can either measure the appearance of B as a function of time, so just the derivative, the change in B over the change of time, right? Which should equal to the change in concentration of A over time, right? So either one would work, and both of these are velocities, right? So this will give me the rate by which the reaction is proceeding. Initially, as substrate concentration increases, the rate of the reaction increases. Eventually, as the substrate keeps increasing, the rate of the reaction will reach a maximum value called Vmax. Remember, reach, it will never really get to it. At this point, the enzyme is saturated, and the rate of the reaction depends on how fast the enzyme can turn substrate into product. The Vmax divided by enzyme's concentration is called the turnover number. So if I take the Vmax and divide it by the enzyme concentration, I get a unique number for that enzyme, which is called the turnover number. which gives me the ability to calculate the Vmax at any concentration for that enzyme. Km is indicative of how tightly an enzyme binds its substrate. A low Km value corresponds to strong binding of substrate to enzyme. A high Km value corresponds to weak binding of substrate to enzyme. Now, this kind of throws students off a little bit. A low Km value corresponds to strong binding of substrate to enzyme, and a high Km value corresponds to weak binding of substrate to enzyme. So let's go back to that graph we had above. So I have two enzymes, and one path is being shown in green, and we're going to go ahead and have another path. We're going to have the Vmax be the same. Okay, we're not really concerned with the Vmax at this point. So I have another one going up like this, very quickly reaching Vmax, and it sort of stays that way. Right, so the Km for this one is going to be right here. Right, and it's unfortunate that the Km is written in, we're going to write this one over it with green for the green enzyme. Okay, this is for this one. Now we're going to have one that goes a little bit slower. This one also reaches the same Vmax, and it sort of plateaus out. And you can see if I go for half a Vmax here, it'll be somewhere here. Right, so this is the Km for this enzyme. Now, what that is saying to you, that whole Km thing and the affinity of the substrate for the active site, for the enzyme. In the case of the blue enzyme, you need much more to get to that state of having half of the enzyme occupied with a substrate, whereas with the green, you need much less substrate to get to 50% of the enzymes being occupied by a substrate. Whereas with the red, you even need less. So if two things bind very well to each other, from what we saw from Ka, that means at low concentrations of the binding partners, you're going to have more of them in the bound state. When the binding affinity is not very high, you need more of the binding partners. Well, in the case of enzyme plus substrate, giving me enzyme substrate, well, one of the binding partners is a constant, and that is the enzyme. The enzyme concentrations are not changing. This is a constant. So the enzyme concentrations are not changing, only the substrate concentrations are changing. So if I need to have much higher levels of substrate to actually have 50% enzyme substrate, then I can say, well, since the blue enzyme requires so much substrate just to get 50% enzyme substrate complex, that means comparing it to the green, which requires much less, then the binding affinity of the blue enzyme for its substrate is much less than the green enzyme. And that's all that is saying. So the lower the Km, meaning that you're moving in this direction, means that the affinity of the substrate for the enzyme is higher. Whereas a higher Km, which means moving in this direction with your Km, means that the affinity of the substrate for the enzyme is less. If the reaction being catalyzed is a very favorable reaction, the reverse reaction can be ignored. Then the following equation can be utilized to calculate the rate of the reaction. So this equation, you're going to see it probably again at some point in your careers. And we're going to be using this equation for some other purpose in section 2. And we're introducing it here now. So this equation can only be used if the reaction is very favorable, meaning that the reverse reaction can be ignored, like ATP hydrolysis. If you can ignore the reverse reaction, then you can use this equation. If the reverse reaction is actually a player in the process, meaning that it cannot be ignored, then this equation right here cannot be used. So we have a reaction. You can think of it as, let's say our reaction is, because we have examples of these type of reactions. Glucose to glucose 6-phosphate, where an ATP is used. And the enzyme is hexokinase, right? HK. This reaction is very favorable, so we can use this equation for hexokinase, for this reaction. So what is the rate of the reaction if S equals to Km? The concentration of substrate, in this case it would be glucose, right, if we were using this. But the concentration of substrate equals to Km. So let's plug that in. So V equals to Vmax, and S, concentration of S equals to Km, so it would be Km over Km plus Km, which equals to Vmax Km over 2 Km, which equals to half of Vmax. And that's what we want. If the concentration of substrate equals Km, then the rate of the reaction equals to half of Vmax. Exactly what we want. What is the rate of the reaction if the concentration of substrate is half a Km? So let's plug that in. So we have V equals to Vmax, and we have concentration of substrate equal to half a Km, so half a Km over half a Km plus Km. And that gives us Vmax. We have half a Km over 1.5 Km, which equals to, so it's 0.5 divided by 1.5, so it'll be 1/3, so it'll be 1, and the Km's cancel out. All right, the Km's cancel out, so it'll be 0.5 over 1.5, which will give me 1/3 Vmax. So you can see as we get less than Km, rate of the reaction decreases. So what is the rate of the reaction if S, the concentration of substrate, equals to 10 Km? So let's figure this out. V equals to Vmax over 10 Km over 10 Km plus Km, which equals to Vmax 10 Km over 11 Km. And of course the Km's cancel out, bing bing, and we're left with 10 over 11 Vmax. So at much higher concentrations, you can see that the rate of the reaction starts to approach Vmax. Okay guys, we're going to stop here and continue later. Thank you.